Hi, I'm Bob Ward from Microsoft and the Azure Data team. Welcome to the second day of the PASS Summit 2020. Now, before we get started here, one of the things I want to make sure you do is fill out your session evaluations. I take these very seriously. I love to see the comments you have, good or bad, about the session today. So please take time to do and fill out your evaluations after today's session, or at least before Friday, November 20th. So what have you got yourself in store for today? Inside weights, latches, and Spinlocks. But what does the returns mean? Well, why not have a good SQL at the PASS Summit? So several years ago, many years ago, I did several sessions at PASS on internals of SQL Server, and this is one of those topics. So as we thought about what we're doing here in 2020, I thought, why not come and bring this topic back? And I think a lot of people will enjoy some of the information I'm going to share today. A couple of logistics for you. Number one, I have my great friend and colleague from customer support, Suresh Kandath, online answering your questions during the entire session. I'm probably going to go the full 75 minutes. This is a 400 level session, it's probably 700 level. I'm going to go hard and fast and show you a lot of deep internals, but Suresh is going to be there to answer questions during the entire session. Now, a couple other things. You want to know, like, where's this deck? Where are the demos Bob's showing us? You see these links right here, which I'll have for you as well at the end of the session on the last slide. At these two links right here are both the deck and demos of everything I'm showing today. And a couple of warnings for everybody there at home. The internals may change over time, so things I'm showing you may be subject to change, and don't use the debugger in production. Please stay safe and don't use the debugger in production. I'm going to show you how to use it today, but it's not something you're going to use in your production SQL servers. But hey, let's get going. So what are we going to do? We're going to talk about the what, how, and why of weights. And we're even going to include some scenarios for Azure SQL that you've not heard of before. We're going to talk about that dreaded latch weight. What is a latch? What does it mean? How might it affect you? And then finally, at the very end, because your brain's going to be melting, why not make your head spin with a Spinlock? Sorry for the little pun there. But hey, is this even valuable for you, all this internals? Yes, understanding weights is good for you. Understanding how weights work and how you might see them in SQL Server can certainly benefit you and save you a lot of time when you're supporting, working, or troubleshooting a SQL Server. So let's talk about weights. What is a weight type? Well, it comes down to this. It's a place in our code where a thread has to do some weighting. And we mark a weight type almost every scenario where our thread has to wait for something. We created this a long time ago in a galaxy far, far away, back when I first started at Microsoft. I remember seeing these weights, and we created them to help us as developers find bottlenecks in the code. And back then, all you had was locks and IO and network. That was about it. But as time has moved on, we kind of went a little bit overboard. Notice here that today, if you went out there today and look at SQL 19 or even in Azure SQL, you'll see some 1,000+ weight types in the engine. And you're asking yourself, why do you have all those things? Because basically, developers, as they go and build their code and added new features, said, hey, if I'm going to wait somewhere, I should expose that there's a wait going on, and I should mark that. Now, just because you see weights doesn't mean a bad thing. And I'm just going to make this one bold statement to you. If you try to go look at something like DMOS weight stats, and that's all you do for a SQL server, that's probably not a healthy thing to do. It's not bad to look at that, but weights can be a very natural part of the engine, and I hope you're going to see that today. Now, I categorize weights myself. This is my own categories. So when you see some weights show up today, you're going to see things like IO, and I call those resource weights or network thread or memory. Or if we just need to synchronize something for locking purposes or latching purposes and a bunch of other scenarios, I call that a sync weight. And then there are scenarios where we force a weight for things like yielding for processing purposes or CPU purposes. Or it could be that we're waiting on an operating system call. So I call those external weights. And we call that internally something called a preemptive weight. And then background tasks, which wait naturally as part of just running the engine, I call those queue weights, even though in some cases, they're based on timers. So you're going to see these terms throughout the discussion today. Now, how does a wait actually work? Well, first of all, I'm not going to go into the depth of how SQL OS works, but you're going to hear some terms about SQL OS. And SQL OS being a non-preemptive scheduling system, whenever we have to wait, we have to play nice in that playground. In other words, we have to make sure that we properly wait and schedule things within the SQL OS scheduling system. So let's look at kind of an example of what that is. So number one, let's take like a blocking problem. You're just waiting on a lock to do a select statement. So we might have something called a shared intent lock with this nomenclature, LCK, right? That's a common thing you're doing for select statement. So if we know a conflict exists that we should block and we know we need to wait, one of the first things we're going to do is we're going to set up what's called an SOS wait info structure in our code, and we're going to mark this wait type as the wait. So anytime now you look at the system, these SOS wait info structures give us guidance in the code to look at them and say, what is the wait type for this thread that's running? And there's also statistics in there about how long they're waiting, et cetera, or what is the wait resource. Now, for the case of like a blocking scenario, this is the method, and you're going to see it in the Windows Debugger. Yes, the debugger will show up today. You're going to see it in this lock owner sleep call. We're going to call that to say, hey, we need to wait because of the fact we're waiting on a lock. So why is that significant? Well, in this code, we're smart enough to use what's called a SQL OS event to wait. And this is when you will see your request in like a DMV go to suspended state. Well, why is a SQL OS event important? It's because that's how we're going to get signal to wake up when this conflict has gone away and we're not blocked anymore. So what happens when this event occurs? We end up calling an actual Windows call called signal object and wait. This allows us, again, for somebody else to wake us up when the blocking is over, and then we can go forward and resolve running the code we need to do and become runnable and waiting. But what's significant here is when we go into this state, it's our responsibility, because of the fact that we're waiting, to wake up the next person on the scheduler. Otherwise, we'd have a deadlock scheduler problem. So right here in this code, before we call this, we're going to wake up the next person on what's called the runnable list, and then we're going to go into a waiting state. And then when we're woken up, what do? We go into this runnable state, and then eventually we go into what's called a running state. So this is kind of the general sequence, and this is showing a blocking problem, but this could occur for anything. Any kind of wait scenario is going to look like this. One that's a little bit different is called a preemptive wait, and I'll talk about that. Okay, so one of the things you're going to see when you look at SQL Server is wait types and timings, and you're often going to look at things in these DMVs. So I thought it'd be important for you to take a look at how do we mark the different columns in these DMVs in the sequence of going suspended, runnable, and running. So first of all, when a worker goes to a suspended state, we are going to start a timer for the worker to say, hey, this is the start time of when we started to wait. And that's important because we got to know the current wait time when we're currently waiting, and we need to know how long we waited to mark things like DMOS wait stats or fire things like X event. So then when we're in the suspended state, we're going to set the wait type and the wait resource, and you're going to see that in DMExec requests. So when a worker is suspended, these light up for you to see what is the wait type and what's the resource they're waiting on. That wait resource can vary depending on the type. And then the last wait type is set to the wait type. Now that's going to become significant because in some cases in DMExec request, you're going to want to know what was the last thing I waited on, what's the current thing I'm waiting on. And you're going to see in things like SOS schedule yield, you only see that in a last wait type, and I'll explain. So then we increment the wait type counter in DMOS wait stats. So now you can see from the perspective of timing, how do I start these things? How do I set these wait types? And how do I increment the DMV that you see for stats? Now, when a worker goes runnable, we mark this in the workers as a resume start time because we're resuming. Now, because of the fact we've gone runnable, we're no longer waiting. So technically what we do is we clear the wait type and the wait resource so you don't see them in those DMVs anymore because we're now in a runnable state. But when we go running, you'll see, whoops, sorry, skipped a little ahead there. When we go running, you can see now that the wait time, the max wait time, the signal waits, all of this stuff gets recorded in the running state, not the runnable state, because there's something called a signal wait time. That can be the difference between these two. Now, what's significant here is last wait time is not clear. That's how you're able to see when you go to a runnable or running state, what was the last wait type I was actually waiting on. You can't see the time of that, but you at least know what the last wait type was. Now you can see how the timings occur. Because we mark these start times, a wait time is the current time minus the start time of the worker. And the signal wait time is the time now when the worker started resuming. So why does that even matter? Because if there's some sort of scheduling problem, this signal wait time could be a long time. And typically what you see in a normal running scenario is that the wait time will be a lot higher than the signal wait time. There's one exception to that, and that is SOS schedule yield waits, and we'll talk about that. So I thought you might enjoy just seeing how would you mark timings and how do you see these various things in the structures and DMVs. We are marking structures in our code, so it'll show up this way. And then finally, I need to point out here that your friend is X events. These two events, specifically like wait completed, that is one way that you can debug almost any wait type. If you have a wait type in your system and you're like, I don't know where this is coming from, I don't know what query is generating this, I can't track it in these DMVs, it's happening too fast, you can use X event to go track anything you need to do for a wait type. Okay, what are some of the most common wait types that I see, and what do they kind of mean to you? So number one is this LCK wait. That's a standard locking wait for page locks, row locks, table locks, you name it. And that's a synchronization. Of course, this is a isolation or a logical concept, not a physical concept. We'll explain later when we talk about latches why it's not a physical concept. But that's the most common thing you're going to see. And when you see this problem, the blocking session ID lights up in things like DMExec requests. This is one you're very familiar with. So latching shows up in the form of page latch and page IO latch, and that's for page protection, a physical concept. And I call that both a sync and a resource wait. And I'm going to defer explaining what I mean by that when I talk in the section about latches. Write log wait, there's no question, if you see high write log delays, it's waiting on transaction log flushing. And that's why I call it a resource wait, because it's usually indicative of waiting on IO when we're flushing log buffers. Now, SOS schedule yield, excuse me, back up a little bit, SOS schedule yield is waiting for CPU scheduling. And I'm going to show you a more detailed slide in a second of how does that actually work. And I call that a forced wait, because this isn't where in the code we are forcing our own threads to wait to ensure we properly schedule all CPU resources across SQL Server. Now, async network IO, you might have seen this before. Whenever I see this, I always tell somebody, we're waiting for a TDS packet back from the client basically to tell us you've processed results. It could be a networking issue, which is why I call it a resource wait, or it could be there's a problem with the client app not properly processing results. And then finally, CX packet. Why do I call this a deceiving wait? Because when you go look at DMExec request and you see CX packet wait and you're like, oh my gosh, I've got a CX packet wait, what do I do? It's just indicative that there's a parallel query running for that request. And so it's a synchronization wait. It's simply used to indicate I'm synchronizing operations between parallel workers for a parallel operator in my query. So go to DMO's waiting tasks to try to find the true wait type of what's going on with these multiple workers. I have an example to show you that. So you see right there, CX packet wait out of the gate. Don't freak out when you see that. Go look at OS waiting task. It just means you're running a parallel query in SQL Server. And then what about background waits? Background waits are simply waits that are naturally there as part of lazy writer and checkpoint and all the background tasks. And there are two types. One, there are background tasks waiting on a timer. So they just wait for 60 seconds, wake up and run again, or they're signaled. So I call those queue waits because typically you're just waiting on a queue for somebody to put something in a queue, you're signaled and you wake up. But again, it could be a timer wait, like a lazy writer where you're woken up every 60 seconds and then you go run and do something. So these are the most common wait types I see in SQL Server and some explanations of how you might see them. Let's talk about SOS schedule yield waits. Why do I call it a forced wait? How does it work? And let's break some myths today about what does this really mean. So first of all, there are tasks that naturally yield in SQL Server. And what I mean by that is when you're waiting IO, when you're waiting on locks, when you're waiting on latches, when you do that, you saw earlier in my diagram, you yield to another thread running on the scheduler because you're waiting on a resource. You wake up the next runnable and you just wait for yourself to be woken up again. So that's great and fine. But what if you're running in SQL Server and there is no waits? There are scenarios where you're doing something and you don't have to wait for anything. If you did that, because we're a non-preemptive scheduling system, you would have a problem. So what happens here, if there's a task that does not naturally yield, we have places in our code where we detect this. And typically on a quantum of 4 milliseconds, if it's exceeded, we yield to another person to wait. Now, if we don't do this right, you see something like this in your error log, the dreaded non-yielding scheduler. That usually indicates there's a problem in our code that we're not yielding correctly. So here's some examples. You can run a query that doesn't need IO. for pages. You could actually go run query that just go after a query, a set of pages in buffer pool cache, never need IO, scan through them, and you're just chewing up CPU resources to do that. You could have T-SQL variables only, or just expressions in your code that we're processing where you don't need to wait on these natural things. Query compilation, hashes and sorts. There are other scenarios here you're going to find in the engine where we're running. But again, we have put in natural logical places to detect these things and to properly yield. And when you yield, this is the wait type you see. So what are the indicators of this wait type? So this is where I'm trying to break some myths. If you just see a count of these, but it's a low wait, this is okay. Even a single query that's running on a scheduler for SQL Server, a single query that doesn't need to do any natural waiting, it always yields to itself. I know that sounds crazy, but because of the way we process things in the background, we need to let even background tasks run, right? Or we need to process IO and various things in the engine. So even a single thread will yield to itself, and you will still see this wait. So if you've got a CPI-bound workload and just a single worker, you might see this wait show up. But a high count, low wait is not a problem. Now, a high count and a high wait, that could be an issue. It could be a lot of CPU queries that are competing, and you don't have enough CPU resources, or perhaps you've got inefficient queries that are using too much CPU. It also could be, though, that you've used resource governor to cap CPU usage, and we might show it up in this way as well. Now, the other thing you should look at is if you've got a very low count but high wait, that could be a problem with SQL Server itself, especially cases where we're not yielding. But there are some scenarios where you have preemptive work threads that are hogging CPU. Something like a task that goes off and has to do preemption to an operating system call, but an operating system call, for whatever reason, is going to CPU spin. That could result in some of these scenarios because it's chewing up a lot of CPU resources. And then RGCPO cap could also result in this, but most of the time I've seen that result in the second scenario. So SOS schedule yield is not a bad thing, but if it shows up with a lot of waiting, it could be indication typically of lack of CPU resources or inefficient CPU queries. Okay, so let me go back up and just wait one other comment here. You only see SOS schedule yield in the last wait type or in OS wait stats. And here's why. If you remember back on the screen, I told you when a worker goes runnable, we clear the wait type. So what we do for a case for SOS schedule yield is, if you just need to yield to the scheduler, is we mark the wait type as we're getting ready to yield, but then we go right to a runnable state because we're yielding, right? And so when we do that, with that wait type gets cleared, but we don't clear the last wait type. Again, this is why you only see this in last wait type, but it does show up in OS wait stats. But hey, let's do demonstrations. Why are we sitting around just doing a bunch of slides in a 400 level session? So what I've got over here, and just to let you know, when you look at my demonstrations, I've got on my other monitor here a README file that I'm looking at. You're probably wondering, like, why is he looking over here? I'm looking at the README file to make sure I follow the instructions very carefully, because some of these are very time-sensitive operations that I'm trying to run, including when should I kick in the debugger. So as I mentioned, this talk is several years back. So what you're seeing is some examples of days when the Dallas Cowboys actually were a decent football team. So these examples are very dated, but it's okay. It all still applies. So I've got a database I'm running right here, and I wanted to show you some of the basics of a blocking problem, what it looks like inside a debugger. So I'm going to run this query just to go ahead and let's see. Oh yeah. Let's stop this because I've already inside my database. I can't drop it again. So let's just go in here and drop the table again, just to make sure we're here. Okay. So what I'm going to do is first I'm going to delete Jerry Jones. There's many times in the world, but I'd actually like to do that. So I'm going to delete him, but I'm going to do it in a transaction state. Now notice the transaction is finished, so the worker is actually done. But let's go insert a new row here, and you notice it's blocked. What does this look like inside a debugger? Remember the lock owner sleep code I talked about? So let's do this. Let's go over into this window over here, and we are going to start the debugger. Now you're asking yourself, like, how do you start debuggers? Well, I've got some command scripts in here to show you how I'm using the Windows Debugger. And here I'm using public symbols to show different symbols in SQL Server, and I'm attaching to the SQL Server process. So let's see what this looks like. So bring this up, debug SQL.cmd. And this is typical what it looks like to attach. Now I've broken into the debugger, and what I'd like to, it's frozen now. Those processes are frozen, but I'm blocked anyways, who cares? So I'm gonna run this command. I'm gonna run bang unique stack, which is gonna show me only the unique call stacks in the engine, because many of these are idle workers where I don't want to see these repeated over and over. So I'm gonna run this, and then what I'm gonna do is I'm gonna look for that lock owner call. So lock owner. Now, if I say I can't find it, it's because my context is at the end, but let's go look upwards. Ah, there we go. So this is an example of the query that's blocking. These parts of the code right here are us making a request in the SQL to run that insert statement. And then if you see it comes along here, notice this is the key part of the call. So this is going into a state to say, I know I need to do a lock, but I realize I'm blocked. So this is, remember we talked about the sequence. I go to this lock owner sleep call, which ends up going into SQL OS. So I need to make sure I play nice with the scheduler. So when I'm going to sleep, I'm using SQL OS to suspend me. I'm in the suspended state. And again, I'm going to wake up the person that needs to run next to go runnable. And then I'm going to go in this waiting state. And so this is very typical right here of somebody waiting on a resource in SQL Server based on SQL OS. Now let's look at an example of something where it doesn't look like this, but you're still waiting. So I'm going to look for resource monitor. Let's look resource monitor. And I need to probably go up to find resource monitor. Aha. So I'm going to scroll up here. This is interesting. Okay, so this is resource monitor, a background task in SQL Server. But you'll notice as resource monitor is waiting, there is no SQL OS call. So resource monitors is here. Sorry, let me do this again. Resource monitor is here. It goes right into a Windows call to wait. Now, you said you had to play nice in the SQL OS playground. What about this code? This is an example of a preemptive thread. Resource monitor by its nature has to check the health of SQL Server. It can't go into the scheduler. It needs to be able to run all the time, but it's okay because it's not taking up resources that are going to block anybody else. So it's an example of what it looks like to be a preemptive thread in SQL Server, but still waiting inside the engine. Okay, one other thing, I'm going to leave the debugger running, so I'm going to hit go here. And I'd like to go back to my query window. And you know what? I'm just going to go ahead and stop these transactions. But I did want to show you this. I wanted to show you what does it look like for these background tasks, because you may be looking at something like DMOS waiting tasks, and you want to see the behavior of these background tasks. So if I run this, notice a couple of things. I've got checkpoint queue here. By its nature, that's telling me that checkpoint, the background task for checkpoint, waits on a queue. So the way checkpoint works is that when somebody needs to checkpoint the database, something is placed into a queue, this checkpoint process is waiting on this queue, and it gets woken up, says, I'll process the request to do it. You'll notice here that the duration for this is really high. That's because nothing's been sent to the queue for a checkpoint to do anything. And the wait time will accumulate until checkpoint has to process. It'll get cleared, and then it'll start again, right? But what about lazy writer? If you run this over and over, you can see lazy writer is like at a higher wait, and then if you run it again, you'll notice that it goes down lower. That's because lazy writer wakes up every minute. And so you can see here that the duration is going to be something that will clear and start over and over and over, because lazy writer is based on a timer. Most of the time you see the timer ones, they'll have this word sleep next to them. So you can see when you pull this DMV over and over, they will go to a certain number depending on whatever timer they're set to, and then they'll come back, wake up, and then start the whole process over and over again. Okay, so that's just a little quick look at basics of debug waiting. What about this SOS schedule yield wait? Let's take a look at that. Let me clear these. And let me reset my README that I want to look at for SOS schedule yield. And again, you have access to all of these READMEs and all the instructions as well. So let's load up some queries here. Let's load up DM exec requests. And you can see I'm showing you a window, the queries I'm going to be loading. So this is me just looking at what does it look like. I'm going to look at wait stats as well. And I am going to, so I've got an X event session. Let's run that. This X event session that I have down here, tracing yield weights, is set up to trace the wait completed event, but only for SOS schedule yield. So I'm going to start that session. Because remember, I told you that's your friend when you're looking at wait types you're not recognizing. And I'm going to watch live data on that one. And then I've got a workload that I'm going to run that just runs a, let's go down here to run it. So I've got this workload and I'm using O-stress for this case. I want to show you what I'm going to run here. This is going to run SQL CPU demo. What is SQL CPU demo? This is just a query that literally just chews up CPU. That's all it does. And I'm just going to run a bunch of users doing this. So let's crank it up and see what this looks like. Now, I have to admit to you that Zoom, which I'm using here, uses a lot more CPU than I expected. So we'll see how this is going to run. So I go to DMExec requests, and I'm going to clear wait stats so I can just kind of see what's going on here. Now, if I run here, this is the behavior I mentioned earlier. Notice that I've got some of these in a runnable state and some in a running state, but the last wait type is SOS schedule yield, but never the wait type itself. This is the example I mentioned that when we yield, and this was happening for these queries, we'll set the wait type, but then we'll go in that runnable state because we're yielding. That's what yielding means. And we'll clear it, but the last wait type remains. This is why you can always look at that to see, oh, have I got this wait kicking in? Now, if you go look at OS wait stats and you order by count, you'll see several of these, but notice here's my SOS schedule yield, and I've got a lot of them, and I do have a fairly significant amount of waiting. And in my particular case, I could keep polling this and see that, oh, I probably am competing for CPU resources here. But this is significant. Notice that the signal time is very close to the wait time. That's a good thing, because that means that actually all the time I'm waiting is the time just to get signal to run. If this was significantly higher than the wait time, that could be a problem. The difference between this and this is the time it takes for us to wait and get signal to run again. So if we have a schedule yielding problem in SQL Server, the difference would be large between these. So that's a look at the waiting test. So let's do something kind of fun here. Let's look at Task Manager. Let's bring this up. Now, I'm almost pegged 100% for these CPUs. You can just see across the board. Let's break in the debugger and see what this looks like. If we dare. Do we dare break in the debugger? Let's do that. Let's break in the debugger. And now let's do tilde. In this case, I'm going to do not unique stack. I'm going to do all stacks. And I'm going to look for a routine called yield and check. See if I can find that upwards. Yield and check. What does that look like? Ah, there's one right there. So here's an example of running a query, and I'm actually doing a hash join. I'm processing a hash, but we know in a hash operation, which is all in memory, we need to yield at a certain point because we've used CPU resources. So you can see here, that's what I'm doing. I'm processing this hash, but we go and say, you know what, should we yield at this point to the scheduler? Because other people need to run. And here's an example of us in this code. We're going to set the wait type for SOS schedule yield, but we're going to go into what we call this runnable state, which causes us to eventually call that same Windows call as when we're blocking. Isn't that amazing? So when you're blocking or when you're waiting on something and you're going to wait, you always go to this call right here in Windows, because that's how you get woken up to start running again. So this is what it looks like to be an SOS schedule yield state. Let's look for another one and see if we can find somebody that's not in that state. Let's see if I scroll down here. Let's see. Oh, give me a second to scroll up. I'm just going to look at some of these call stacks. These are all threads running in SQL Server, and I'm kind of looking for one that is not waiting. So if you keep, and it's a timing issue to see where I catch this. These are all waiting. These are all waiting. Aha, here's one that's not. So this one's doing the same hash processing, but guess what? It's already yielded. So at the top of this call stack, if you look here, you can see that it's in the middle of running some code. I just caught it in the middle of running some execution. So this is an example of a thread that's in a running state right now. So that is SOS schedule yield waits. I'm going to let the debugger kick back and show you something fun about resource governor. So go back to Task Manager, and you can see now that I've unfrozen SQL because I've continued in the debugger, it goes back to this crazy CPU state. But let's say that I'm like, you know what, on the fly, I want to limit what this can do. So I'm going to come along and I'm going to open up a file here, and I'm going to cap CPU resources for the entire SQL Server itself to 5%. So I'm going to run this, then I'm going to come down and I'm going to see what happens in Task Manager. And you'll see we're back to a much lower state. Now, by the way, a lot of the CPU you see on here is Zoom doing this video feed. So normally without Zoom, I would see this down to like something like 2% in SQL, but you can see the drop in this. And then I can come back and I can say, well, you know what? I just will uncap this back to 100 and let them go. So let me go here and uncap everybody, and boom, go back to your Task Manager, and we start climbing back to 100%. So this is showing you the dynamics of how Resource Governor can truly cap. And what's happening is Resource Governor, by capping things, just allows our yielding code to take longer to run, right? We take longer to actually yield and be runnable, because that's how we're capping how much you can be scheduled for CPU resources. So that's kind of a fun demonstration to show you how yields work and how weights work with SQL. All right, let's go ahead and stop this demonstration because my fan is starting to kick in on my computer. I can hear it loudly here. And let's get rid of these queries. I make sure I'm back to cap because you don't want to be capped at a 5% when you run the rest of your demos. Now, one last thing I want to show you here. This was the X event. Look at that. You see these wait completes all kicking in, and here is the wait type of SOS scheduler yield. You can see things like the signal wait, what scheduler, notice all the different schedulers that are showing up here, and it's session IDs. And I've put the SQL text next to these if there is a SQL text. One thing about wait complete that's nice is that if it's a background task, you can also see that, and there would be no SQL text, but you can see it through the session ID of what the session is related to that wait. So let's go ahead and stop that as well. And we will stop that X event session. Okay, so that's a pretty good look at weights. Let's go and go back to our deck and let's move on. Now, let's talk about some other weights you might see. Number one, if you see the word latch and something else, this is something other than a page latch. We call this a non-buff latch, and we'll explain more about that in the next section. What about preemption? So this is an interesting one, and I'm not going to show an example here, but I've got examples in other slides that you can look back for other talks I've done. And that is, whenever we have to wait for an operating system call through the Windows, and this is not operating system calls for the normal part of yielding. This is like writing out to a file or something like that. When we have to do that, we have to go into what's called preemptive mode, because we don't know how long it's going to take to wait. You see, in SQL Server, if we're waiting on ourselves with a blocking problem, or we are waiting within our scheduling system, we kind of control the overall waits that are going on. But if we call an operating system call to go look up Kerberos for authentication, we don't know how long it's going to take. So we have to go what's called to a preemptive state, where we're not part of a scheduler. We move off the scheduler. And you saw Resource Monitor doing that naturally. Other threads could do that as part of doing something like a write file call. I call that an external wait, and it shows up with this word preemptive. And what's kind of cool about it is the word after preemptive usually denotes the operating system call itself. So you can kind of see what's happening. Now, a header sync commit wait shows up naturally, and it's normal as part of being synchronized for AG replication. So you will see scenarios where using AGs with secondary replicas that are synced, where this wait type shows up and a write log also show up, because write log is the local log flush, header sync commit being the actual synchronization to log blocks to an AG replica. Resource semaphore is an interesting one. This is being throttled on memory grant limits. If this shows up a lot with a lot of waits, go check out and see what your memory grant settings are, or go find out, am I running a lot of hash joins, sorts of that nature that are requiring memory grants? I need to go debug that kind of type problem. I still call that a resource because it is a finite resource for memory grants. IO completion is interesting. I thought I'd add that here because if that shows up a lot for you, that's indications of IO spills in TempDB. It's not a write log wait. It's not a page latch IO wait. It's spills, because those spills are pages, but they're not true pages in the sense of page IO latching. So that's why it's called an IO completion wait. And then thread pool is an interesting one, because if you run out of worker threads, this might show up, but only in DMOS waiting tasks, because you don't have a request yet, so it can't show up in exec requests. But note this one, if this is showing a lot for you in OS waiting tasks, go look at your system. You probably have enough worker threads, but you've got a long blocking problem, or a lot of queries are just using a lot of CPU utilization and they're just using up worker threads. A lot of times it's not the fact that you don't have enough worker threads. It could be in some cases, but that's what a thread pool wait is. And then log rate governor and RBIO weights are very specific and unique to Azure. And I'm going to show you in a second exactly what that is, but these will only show up when you're using Azure SQL database or managed instance. So in fact, and you just look at the list here, there are a bunch of others. There's 1,000 of them, right? In fact, I'll just make a call out to Paul Randall. He's done a really good job on his blog and his website for SQL Skills to show all the different weights and tracking that he's done over years of what they might mean. Okay, let's talk about this transaction log governance that we have in Azure that I just mentioned. So I'll walk you through this a little bit slowly because it's important you understand it. So in Azure, you have your SQL Server, Azure Database or Managed Instance running on what we call a primary compute node. That's what the P means here. A SQL Server running on a compute node. Now in hyperscale, we'll talk about in a second, we have on that same node something called a log throttling service, which we'll show you what that means. So what we've done in Azure, in order to meet service level agreements, is that we have coded an enhanced resource governor to have what's called transaction log rate limits. The limit is based on a cap. That cap is based on something called a service level objective, which is your combination of picking things like general purpose and vCores or business critical or different options of how to deploy Azure. And you can look up what that cap is by looking at this DMV, which is unique to Azure, this primary max log rate. You can monitor the usage of this through another DMV, 2 DMVs that are unique to Azure to see how much am I using based on the rate itself. So basically, when you do an insert in SQL Server, because this is just SQL Server, we need to generate log records as part of that operation. And what we do is, in Azure, is we take a look at this log generation code and we say, hey, is the log we need to generate, how is that matched up with the current rate and bytes that we're using across time? And if that generation is going to cause us to exceed this cap, which is the current limit, you're going to get back a log rate governor weight to your code. Notice this happens very early on, because when you come off this weight, when you're free to actually keep processing because the limit has not been reached anymore, we actually go through and build the log block and put it into log cache. This all happens before the log cache works or things are written out to the transaction log. Now, the log writer is responsible for actually flushing log blocks. And so after log rate governor weights and after the log has been put into cache, when a flushing occurs, that is the true write log weight, whether it be in Azure storage or local storage or whatever. I thought it'd be important for you to see what is the difference between rate governor weights and write log weights. Now, I mentioned about hyperscale. Hyperscale has all sorts of components in its architecture, and these are all applying log changes. So we want to make sure that these things don't get behind. Denzel Ribeiro calls them actors. The log, xlog process, page servers, replicas, and even writing up to long-term storage. If there's behind in their processing, this log throttling service can take the log cap and take the limit and reduce it. And when that happens, you're going to see something called an RBIO weight. And the weights in there for RBIO are very specific to whether it's an xlog problem or a page server problem, et cetera. Now, in addition, in things like, for example, business critical, where we're applying availability groups behind the scenes, if things get behind there, we also can lower this limit from the cap because the cap remains the same. And those weight types I've got documented when you get this deck to see what those actually look like. So this is an example of how you can see these weight types specific to Azure based on transaction log governance. And in fact, let's stop and go take a look at a demonstration of that. So let's move over here to a VM I have, and let's go move that here so you can see it. Now, what I've got over here is I'm in an Azure VM. I'm using Management Studio, and I'm connected here to a couple of different Azure databases. One is a general purpose database, and one is a business critical database. Now, in this particular connection, I can use that DMV, which I mentioned, to see what is the current limit of my log. Now, I've got, based on my SLO or service level objective, which to me, it says here is a general purpose right here, general purpose, 8 core Gen 5 hardware. That is the basic of my rate. And you can look at our documentation for the fact that if I up my vCores in general purpose, I might get more log rates. You'll see in business critical that those log rates could be higher because of the fact you went to business critical. So I'm going to clear my weight stats to show you this demonstration. And then I'm going to go off and run a workload. Now, what's this workload? It's just doing a select into. Now, this is important if you're trying to try this at home. This is a select into that by its nature, because I'm on an 8 CPU, can do parallelism. So I'm going to run this, and then I'm going to go back over to log governance, and I'm going to look for weights. And you can see here, I can see log rates showing up, but notice that I've got exec context ID in here, and I'm using OS waiting tasks. Why? Because this is a parallel query, and that CX packet wait would show up in exec request. That's not very helpful to me. I wouldn't see log rate governor there. So if I just run this over and over, I can continue to see as this executes what this looks like. Now, this is probably done or almost done by now, but if I snapshot and keep looking at it, I might see a few still show up. Now, what about overall are we hitting our limit? We have this DMV, DMDB resource stats, that if I run this, this is going to show me, am I near my limit? And sure enough, you can see I'm just about at the limit. But I mentioned I can also see log usage by using this DMV specific to Azure. And again, you have all the code available to you. If you go to the resources I pointed out, AKMS, Bob SQL demos, you don't take screenshots of this stuff. You have it all available so you can run it. Now I can look at this to see what is my usage compared to my limit. And sure enough, you can see I'm really close to what that actually looks like. And then finally, I can go into OS wait stats and I can tell that I'm getting about almost 3,000 waits. Now it's finished and it took around 47 seconds to run this, 47 seconds to run it based on, and a lot of it's based on the waits for that log governance. There's even a perfmon counter for you to look at log governor use. So you can actually go through if you want to run this query in Azure and see that. Okay, that is the general purpose one. What about business critical? So if I go over to business critical here, which is the same 8 core, I can see here that my log rate is significantly higher than I'm allowed. This OP means business critical 8 cores. So let's see what it looks like now. Let's clear our wait stats. Same table that I've deployed in that database. I'm going to run the same select into, and I'm going to go over here, and I'm going to see what does this look like now for my log waits. Now, if I run this, I might see some show up. I still could get throttled on this log scenario here as I'm running this. And you can see here's one that's going to show up, and it's still running in parallel. But I don't see as many of these running. In fact, so I run this again and again, I'm going to see this just kind of goes away. And if I go to my resource limit, I'm going to hit near the limit again. You see it at 97%, but only like one time. And even if I go down and look at how much log I've used, you're going to see it's a lot less for a shorter period of time. In fact, these log rates you can see are a lot less significant than I had before. Now, what does the overall wait stats look like? If you run this, you can see here I had 3,000 before, only 685 now. That's because I was given a higher log rate. Now, I want to just tell you one thing. It's not that you're going to go to Azure and hit these log rates all the time. In fact, a lot of times you can't generate enough workload to hit the rates. I happen to pick a bulk operation like a select into that runs in parallel, all trying to generate log usage. In this particular case, if these were not running as parallel queries, I would have never come close to hitting my log rate limit. Okay, that is an example of what it looks like for log governance in Azure. All right, so I'm looking at my clock here. We've got about, I don't know, 30 minutes left to keep rocking. I hope maybe at this point, I don't know where you are in the world right now, you're saying to yourself, this is pretty fast. He's really going through a lot of stuff. Let's crank it up, shall we? All right, so let's go talk about latching. In SQL 7.0, brilliant people like David Campbell came along looking at our engine and said, you know what? In order to support things like row level locking in pages and to support other operations, we need to introduce something called a latch. So what is a latch? A latch is all about physical protection. Here's what I mean. A lock is about logical semantics. So you have page locks and row locks, which sound physical, but you have table locks. That's not a physical thing. That's a logical thing mapped to some data in a file. You have a database lock, right? So locks are about isolation level semantics, transaction consistency. Latching is all under the covers to physically protect a structure. In fact, it is used for thread synchronization for important data structures or concurrent sensitive code. So it's something that's a SQL thing. In fact, when we built latching, quite frankly, I remember because I was back working in SQL in the days, we built this so that you would never see this actually. As it turns out, there are important indicators of seeing latching that might be scenarios you need to look at. So it is important to see, but we originally built this, it was not so that you would ever see it. So there's no isolation level or transaction semantics about it because it's a physical thing. And there is an ownership and weighting structure. We need to do that so we don't run into a dead latch. I know that's an actual term, right? And there's a compatibility matrix. There's exclusive latches, shared latches, and you see these show up with SH, EX, etc. And then there's no control you have here. So if you run into latch scenarios, which we're going to talk about in a second, it's not like you have a latch hint. Like in some cases for locking, you can use hints to change behaviors, but for latching, you have no direct control over this. But you have implicit control, and we'll talk about why that may be. Okay, but what is this really? What is really a latch? Well, what it is, it's a C++ class in our code, and it looks something like this. So in the beginning of this class is a list of waiters if anybody's waiting. It's literally a list of tasks. So we know how to go wake up people when they're waiting on a latch. And then we need to put in the task address of the owner. So tasks, by the way, are mapped to workers, like running a query. And so in here is an actual memory address of a task in SQL, somebody who owns the latch. Now, then we have the actual latch itself, which is a long value, and it's something called a bitmap. And you're like, what's a bitmap? Well, we take this actual value. Sorry, let me come back down here. We take this actual value and we break up this integer into these bits so that when we want to see, does anybody own the latch, we can see by the bits are set to see, is it an update latch held, exclusive latch, and what's called a destroy latch? Are there waiters? We even have a Spinlock to protect the latch itself. We'll talk about Spinlocks later. And then there are other things we put into this integer. We pack a bunch of information in an integer and use bitwise operations to find out what is it about the latch. And then near the end of the class itself, the latch class, we mark what's called the latch ID. And we'll talk about and show you how does a latch ID correspond to something that you see in form of a latch. So in the end, a latch itself is just a C++ class that we carry around and use to do physical protection. Okay, so let's talk about page latching for a second, because when you think of physically protecting a page, what it really is called a buff latch. Like, what's a buff latch? Because that's how it shows up in some cases. Some cases we use the word page latch. In some cases we use the word buff latch. So what we have is we have a system for reading pages, right? Writing pages, traversing pages, freeing pages. And usually it shows up in the form of page latch and page IO latch. I'll explain the difference between those in a minute. Now, internally, it looks like this. You have a buff structure. And in this buff structure itself, a memory structure, you have a page pointer to the page itself, a page number. Sometimes we just want to shortcut and go to the page number in the buff structure, a status to show us what is the status of buffers, and a latch class, like I just mentioned. So the latch is used to protect this buffer structure. Now the latch has these different bits, and this is important because it tells us, has somebody changed or dirtied the page? Is the page in the middle of IO? Is the page currently hashed? Is it being read? Is it on our LRU list? This is a series of bits that we can detect what is actually the status of the page. And you're like, well, Bob, where's the page? You're just showing me this buff structure. Well, as it turns out, this is how it works. This right here, this is a pointer, a memory address to the page in cache itself. So it points to the start of this page, which you've seen before with DBCC page, with a page header and a page ID. But again, we shortcut page ID and mark it in the buff structure as well as what's in the page header itself. So whenever you're looking at page latching, what you're really looking at is SQL Server using this buffer structure, which points to a page, to control synchronization here, which indirectly controls synchronization here. And I mention that because you're going to see the word buffer latch show up sometimes. You're going to wonder, what's the difference between this buffer latch and a page latch? Now, in addition, in SQL 19 and now in Azure SQL, you can use these new page functions, because a lot of times you're looking at a wait resource for a page latch as DB ID, file ID, and page number. And you're like, what the heck is the object that belongs to that? I can't see that in DM exec requests. We'll show an example of how you can use page functions to break that out. Okay, thought you might find this interesting because people have asked me this question. So I thought we had row level locking, Bob. We have page locking. Why do I need a latch to protect a page? This is representative of a physical page in cache or in disk. You have, and it doesn't represent all the pieces of the page. You have a page number, and you have something called free data. Free data is a pointer to where in the row can I actually add new data? Where is it possible to add to the row new data? And you see here, these are values in the row itself. And then at the bottom is something called the offset table. These are byte offsets of where things exist in the row in the page. So let's say I do an insert of values for a row in SQL Server. I'm inserting rows of SQL Server. Sorry, just to be clear here, these represent rows on the page, not a single row. So 100 is one row, 200 is another row. So I didn't need to insert a new row. And if I don't have latching, it's not a problem. I just go look at free data and I go stick, as you see in the right-hand side over here, I go stick in values of where they belong on the page, because free data tells me based here, where should I do that? Looks great, right? So what if, from a thread concurrency point of view, because two threads could run on two different CPUs, another thread comes along and tries to insert 400. Well, guess what happens? Free data over here, before this insert is fully complete, still says 126. So this thread says, no problem, I'll just write right there. That is an issue. That is an issue because you've lost data. So how can we see it a different way? Well, let's do it this way. Let's back this off and say, let's say when this insert has to go insert this row, that as part of its operation, it gains an exclusive latch on the buffer pointing to this page. Now, when 400 comes along, and so it's going to go ahead and put its row in there of 3 and 300, and 400 comes along at this point in time and says, I also am going to do this, but it needs an exclusive latch, so it's blocked. It's waiting until this first insert finishes. Well, what does this insert need to do to finish besides putting the new row in the page? It needs to come along and put in the offset table of where this row exists and then mark where is the space on the page for the next row. And so now it can get rid of its latch. This can come along, it's free to go. Now it knows exactly where it should put its row, and we're all happy. So this is a great example, a simple example of why latching is required to physically protect a buffer which points to a page. Okay, so what about IO latching? Because people have asked me, I thought page latching was an IO thing. Well, not necessarily, because that was an example on the previous screen of a page latch. Well, here's what an IO latch actually looks like. So when a worker thread comes along and needs to scan a table, it needs to get a page. Hey, I need page 100. And we know that based on metadata we have about where pages are in relation to things according to indexes or pages or tables. So when I get a page, I could determine that that page is not in cache. Our code knows and says, oh, I don't find buffer pool cache. I need to bring it into cache. So what do? We go acquire an EX latch on that buffer when we determine that the page is not in cache. So this is pointing to the page on disk at this point. Now, what we do is we are going to submit an asynchronous IO request to like the operating system to go get this page, and we're going to mark in the buffer structure buff IO. Now, what happens next is very crazy. We are then going to try to get a shared latch on the same buffer. The latching system understands that even though you're the same person, you're going to get blocked. And our code says when you need to get a page latch and you're waiting on that latch, if the buff IO bit is set, mark it page IO latch instead of page latch. So that's the distinguishing factor. When you're normally going after a page and you're waiting, like I showed you in the previous screen, it's just page latch. When you go after, and we know the buff IO bit is set, we know it's an IO latch. So what happens next? The IO completion routine is successful. It could be a different worker thread that processes that. It goes and it clears the buff IO bit. It releases the latch. And now the shared latch is required by this worker, and all is happy, and you can now get the page. So this is even a single worker that just needs a page from disk. A page IO latch is natural. Anytime I go read a page from disk, I'm going to get a page IO latch. It is the wait time that's significant to show you the latency of how long it takes to do that. Okay, let's talk about some other latches, and then we're going to do a demonstration. I mentioned earlier that latching is about thread synchronization, right? So DMOS latch stats shows you some 170 non-buff latches. Well, first of all, let's talk about TempDB buff latches. So TempDB buff latching or latch problems with TempDB are typically not IO problems. In fact, you typically don't see page IO latch there. You just see page latch. And that's because allocation pages and system table pages can be contention points for you based on all the different temp tables you're creating. And we give you advice about how to create multiple files to alleviate allocation page contention. And then at the bottom, you can see we've introduced something called TempDB metadata optimization to reduce the need for contention on system table pages. But every time you see a TempDB buff latch or page latch problem, it's not an IO issue. It's typically one of these. Non-buff latches show up in the form of latch underscore EX or SH or something. And it's the same latch code, that we use for thread protection. A good example of this, when you go look at an example of looking at latch types or wait resources for latches, is FGCB add remove. You're like, what the heck is that thing? When we do an auto grow, we need to protect a structure called an FCB structure, because what we're doing is that structure holds the size of the file. So when we're growing a file, we may need to change the size in that structure. And somebody coming along also may need to see how much space is available, which is also in that structure. So you may see in a long auto grow scenario, people waiting on this latch because we're both trying to interrogate the structure that holds this information and trying to change the structure to do the actual auto grow. And unfortunately, the latch is held during the duration of the entire auto grow, which is why it can cause actually a problem. And then I indicate here that in the DMVs, the wait resource is the latch type itself. And then we also have something just very quickly I want to mention called super latches. You may find these show up in perfmon and an X event. This is under the code, us knowing that there are hot latches that occur in multi-NUMA, multi-CPU systems, and so we can partition them. We can actually build latches based on a CPU or NUMA node, and we have a concept called a sublatch. Not showing you a demonstration of that, just getting you aware that in some cases we need to partition out latches for hot memory structures across CPUs. Okay, let's go take a look at a demonstration of this. All right, so back to where we are in our different repros. Let's go spend time looking at buffer latches. I have another demo that I'm not going to be able to show you today on just debugging the auto grow latch scenario, but you can run that offline. I've got all the scripts available if you take a look at that. So for the buffer latch demo, I wanted to show you this. Let's bring up back to our SQL Server. Let's look at how that B stat works. Remember that I talked about the fact that we have that buffer stat. Let's go to latches, and here's buff latch and buffer and pages. Okay, so the other thing I want to bring up here, though, at the same time, to give you an indication of what I'm doing, is this right here. This is an image of those bits I mentioned, right? Different bits I talked about. So first of all, I'm going to run a DBCC page against a PFS page. It's a fixed page in master. And I'm going to run this. Now, one thing in DBCC page you normally do is you just scroll down and start looking at the page. But at the top here, you may have missed the fact that we dump out the buffer structure associated with this page. Remember, that's what we're latching. And you can see here, this is a memory address, which we'll look about in a second, what's in this buffer structure. And if you look here, here is the address of the page I mentioned, but also the actual page number, which I said we'd also put in here. And here is the buffer status. So what is a 9? And if you look over here, actually, I can just put it in the comment codes. A 9 is this in binary. So a 9 is, if you do it in binary, is going to be 2 to the 1 and 2 to the 4. So what does that mean based on that map I showed you? It means buff on LRU and buff hashed. That's just a normal buffer that's in cache. What if I dirty the page? Well, how do I do that? Well, for PFS pages, no problem. Just go create a table and put some data in it. So if I do that, because we have to change the PFS page to mark things are allocated, I can dump this out again, go down here and see that the B stat has now changed to a B. Well, what the heck's a B? Well, let's look at it in binary. Notice this extra 1 has showed up. That extra 1 is buff dirty. That means that I've made a change to the page. Remember, I said the fact that we would mark these changes accordingly. And it could be buff IO, but it's hard to show you a buff in IO in flight. So this just shows you that a page is dirty. Now, if I run a checkpoint, what do we do? Checkpoint, we write it to disk and we clear that bit. So I can run this again and I can look in here and I can see that now it's back to a 9. Okay, so let's go look at a different scenario. Let's show you those first of all, let me just jump into the debugger and show you real quick here. So this memory address right here, that's that buffer structure that I mentioned. So let's break into our handy dandy debugger here. Let's break into here. And what am I going to do? I'm going to do a DD command, which dumps out a memory address. Now, what is hard to see in this situation, I'm going to bring this up here. Remember I said that very first part of this memory address is the page itself. Now you can see here, here is that page. This is a pointer to the page, right? Let's bring back our debugger here. Okay, so these are byte swapped, but this effectively is the same thing as that right there. That's that pointer to that page structure. Now you said also, Bob, that there's a latch class. Well, as it turns out, that latch class is some hex 90 bytes plus what we have here. Let's go 90 bytes down. And what you'll see if you look at this latch class is a bunch of zeros at the beginning. You're going to see here, though, down in the latch class, this 1C. And I just happen to know, because I showed you in that slide where everything is in the latch class, this is what's called the latch ID. So if I do a question mark 1C and I see 28 and I say go again in the debugger, I can go over and do something like this. 28, remember it was 28 was the value. I can go over and I can see find latch class, and I can see from X event that 28 is indeed buff. But also, if I look at OS latch stats, I can just use the row number here to find out 28. So scroll down here, here's 28. Indeed, that is buffer. And latch class shows you all the latches in the system, including buffer latches. Okay, one of the things I want to show you was this page info where you can take a page resource and find out more information about it. So in order to do that, let's do this. Let's go ahead and bring up a database called Go Baylor Bears My School. And in here, I've just got notice I've got an identity column though. So I've got an identity, so that clustered key is going to be increasing all the time. So if I do a bunch of inserts to this thing, what's probably going to happen is I'm going to go ahead and hit a contention point at the end of the clustered index. So let's go bring this up. Let's find exec requests, and let's bring up page info. Page info being the new ability to take a look at a page resource, which again, the wait resource for a page is in DM exec request, but it's only in that database ID, file ID, page ID format. I want to be able to crack that out and take a look at it. So let's go run the workload here. And I've got a command to do this. And let's go over here to do it. I'm going to use my favorite stress again to do that. So insert, this is just going to do a bunch of inserts in here. And I'm running and I take a look at this DM exec request. Sure enough, if I look at this, it's going to show here is page latch, not page IO latch, page latch. But look at this. Here's my wait resource. Well, what is that? If you just look at this, you have no idea what object this belongs to. Aha, along comes these brilliant system functions. So now I'm going to run this and I'm going to run a same query against exec request, but break out the page. Well, look at that. I can now see page ID and I can tell what is the object name. But here's what's really cool. We actually give you access to the entire page header itself. Anything in the page header, you can go to take a look at. Has it been checksummed? Is it a PFS page? You can see status about a PFS page. You can do all sorts of really cool debugging of pages in SQL Server just by passing in page resources. I thought you might find that interesting to take a look at that. Okay, let's make sure we're set for the final push here because we're going to go talk about Spinlocks. Okay, we're going to make your head spin. By the way, that's a shameless plug for when I did this talk years ago. Somebody got on social media and said, I got out of Bob Ward's talk talking about Spinlocks, and I think my head is spinning. If your head is spinning at this point, I have achieved my goal. All right, let's go back to our deck. And again, I also have a separate demonstration that I'm not showing today that you can go look at to see an auto-grow scenario to see what a non-buff latch looks like. Okay, what about this Spinlock thing? A lot of people have maybe seen this term with SQL Server over the years and I've wondered, like, what is this? So first of all, this concept's been around for a while, and I've got a link to a pointer on Wikipedia where you can learn about the concept in computer science of a Spinlock. But it's really interesting. The concept is, how can you be running and waiting at the same time? Which is really what a Spinlock is. So it is possible to consume CPU for thread synchronization. And the concept is you spin while you wait. Now, it can be a dangerous thing to use. It's got to be used correctly. And in fact, why do we even do this? Well, it's a much lighter and faster method than, say, a latch. A latch has a lot of overhead, perhaps, to it for something we need very, very fast. There is no kernel time required for a Spinlock. So what does that mean, Bob, for SOS scheduler yielding? It means that when we're spinning, you're not yielding, which is why it can take up CPU resources, and if we do it wrong, can cause issues. We typically use Spinlock to protect lists and hash tables and various things of that nature. It's all about thread safety and a very lightweight, fast approach. Now, while you're spinning, you control the scheduler. Again, you're not yielding during this. But we're not stupid. We have scenarios called backoffs, and backoffs allows us to switch to somebody else. We could actually yield to the CPU to other threads running on the processor outside of SQL, but we also can back off and sleep for scheduling from a CPU perspective for things to run on our scheduler. So we do have the ability to do that if we need to. And then, could this cause you a problem? Like, do you even care about this? Well, you do. And here's what's really interesting about it. When a Spinlock problem happens, and I've seen this before when I support customers with cases before in the day when I did support, is that you get a high CPU utilization in the SQL Server process, but typically there's no query showing the problem. You know, when you see a CPU issue for SQL Server, you go after, what are the queries that are taking the most CPU? Well, for Spinlock scenarios, we don't accumulate that as CPU, so you don't even know that. And they're usually hot lists or areas of the code that we might not have partitioned properly. And again, like a latch, you don't have explicit control of this. You're not supposed to even know about it. There is no Spinlock hint. Okay, but we do expose some things. Of course we do. DMOS Spinlock stats can show you these things like collisions or backoffs and those kind of natures. So let's show you a little bit of a diagram of what does it look like to have a Spinlock in the code. Like, what do we do? So when we need a Spinlock, we go through a process of attempting to acquire this Spinlock. And we use what was called an atomic instruction to compare and swap whether we need the Spinlock. And a 0 for the value of the Spinlock means it's not in use. A greater than 0 is interesting because it means it's in use, but we also mark the thread ID of whoever has the Spinlock. So the Spinlock is, like anything else, a structure, and it has a type, which is kind of cool because we can see what kind of type it is, and a long value, which is the actual Spinlock we're comparing and swapping or sticking the thread ID into. And this type, by the way, is equivalent to an ID value that maps to a name that you can recognize. Now, the compare and swap is based on the interlock compare exchange algorithms, but that is an atomic operation in the code. That's not going to require any kernel switching to actually do that operation. So if you attempt to acquire and you can't get the Spinlock, that is marked as a collision because somebody owns the Spinlock. So what do we do if there's a collision? Well, we spin. And what I mean by that is we do a loop in our code, and we can call this yield operation, this yield function. Yield is an intrinsic in a compiler that tells the operating system, become preemptive now. Let somebody take over the CPU if they need to, because I want to play nice within the entire operating system scenario. And as we spin, each time we go through this iteration of spinning, we mark that as a spin counter. And what we're going to do is we're going to spin to the limit. So we're not going to spin forever. We have a limit that we denote to spin. So what if we hit this limit? We try to go acquire the Spinlock again. And if we can't get it, we will go into what's called backoff state. Backoff allows us to switch to other threads on our scheduler or go into a sleep state. And a sleep state for a very long period of time is called a sick state. And we have other ways to denote this. Backoffs that are accumulated are counted in our OS Spinlock stats, and we have an extended event called Spinlock backoff. In fact, if you talk to people like Suresh and they're looking at a Spinlock problem, sometimes they'll use this Spinlock backoff event and get a stack dump of what's going on in the code to find out what Spinlock is happening and why is it causing a problem. And then a backoff warning is this sleep scenario that's in this bad situation. So a really bad backoff is a backoff warning situation. Okay, and then what happens when we back off and we still can't get the Spinlock? We increase our limit. Okay, so we're going to spin more and we go back to the spin code again and try this all over again. So spin, we can't get it, acquire it, back off over and over and over. So you can see that if you see a lot of backoffs for a particular type of Spinlock, there's probably a problem going on in SQL Server. Okay, so let's go take a look at one of these lookalikes. We have here about 7 minutes to go. There's a lot of pressure, 7 minutes to go look at a Spinlock. How do I do that? Okay, so this is a fairly intricate scenario to set up, but I think I can do it pretty quickly. So let's do this. Let's go over here and I'm going to restart SQL Server. Now, this is getting tricky now. You're like, Bob, restart SQL Server. What are you doing? So I'm showing you a Spinlock scenario that we fixed, but I have a trace flag I can use. Don't use this as home, kids. If you look at this trace flag here, I have a trace flag I'm going to use to back off the fix so that we don't partition what's called the lock hash. This is the lock hash scenario that we had in the past. And I'm going to take a scenario with SQL Server where I'm going to run it without this fix in place. So let's stop our server and let's start it up with this trace flag so I don't have this problem. So The first thing I'm going to do, though, is I'm going to bring up, while this is starting, some queries. Okay, let me bring up exec requests. And let me also bring up get Spinlocks. I think the server is still starting on me. That's why I'm running into this problem here. Oh, I know the problem. Ha! Debugger. Need to get rid of the debugger. Sorry about that. There we go. Now we're started. I was attached to the debugger and it couldn't start because I was attached. Okay, so let me also bring up get Spinlock stats. Okay, and then let me first run this. This particular code here, connect me, is just going to do a bunch of connections. So I'm going to start him. Connect me. It's going to start a bunch of connections that are just going to connect and hold their connection to the database, which is going to actually put pressure on this lock hash Spinlock, which again, we fixed over time. So then I'm going to run another one that's going to do SP reset connection in a very aggressive way. So let's run this person, and then let's go see what's going on. Let's go look at exec request first. You're going to see here when I run exec request, a bunch of runnables. Okay, a bunch of runnable scenarios with our schedule yield. I'm not seeing anything that's obvious except just schedule yield problems. And that schedule yield is probably because I'm backing off. Well, is that true? So go look here. Sure, look at this. Lock hash. Whoops, well, that's not what I meant. Lock hash here with lots of collisions, lots of sleep time, and lots of back off. And I keep running this over and over. I will see that is the case. I'll just keep seeing this back off increasing. Okay. Now, what about CPU? If we go look at Task Manager, we're chewing up a lot of CPU. But what if you go look at something like this database is called Lock Hash. Now, I'm doing a lot of CPU here, so let's see if this expands correctly. And I'm going to look at Lock Hash Me. And if I go look at Query Store, I'm going to find in Query Store that I don't have any query that really is using up CPU. Like there's nothing to point to as a query problem. So what am I supposed to do? I look at this lock hash Spinlock. I probably need to call a guy like Suresh to actually solve this problem. And in fact, that was required to solve this issue because this was an issue where we were not partitioning this hash across our code. All the threads are going after one structure in this code. What does it look like in the debugger though? Let's go look and see. Let me go back over here. I got one window available to me. Debug, yeah. Now let's see if the debugger attaches, because sometimes when you do a lot of high CPU scenarios, it takes a while to attach. Because what I want to do is I want to set a breakpoint on one of these backoffs just to show you what it looks like in the code to back off a Spinlock. Let's see. I know we only have a few minutes here. We'll see if this attaches with all this CPU utilization going on. I probably should have done this before I ran the workload. Okay, it did break in. So I'm going to set a breakpoint on that code because I happen to know that's the code that we do backoffs on. Let's save that. Okay, and go. And boom, I hit one right out of the gate. And I hit it. I can see here, this is actually one of those scenarios. And this is the code that's going after that Spinlock right here. Now, it turns out, if you see this number 156 right here, and if we were looking at a call stack in CSS, what we can do is we can look at 156. Let me go in the debugger. I can come back over here and I can go into extended events and find out what is 156. Well, 156 is indeed lock hash, if it'll ever come up here for me. Actually, I didn't go in the debugger. Oh, let me disable my breakpoint and go. Oops. Okay. Woo. Yeah, I'm really hammering my system. There's lock hash right there. So we can see what a Spinlock looks like and a breakpoint in the code. That's an example and demonstration of Spinlocks. I know we're about 2 minutes away from finishing this. So quick summarization, let's sum it up. Besides your brain leaking out and melting and hurting, weights are an important part of debugging performance problems. And I showed you all these scenarios and how to do that with SQL Server. And it's very important to understand the difference between a page and a page IO latch and non-buff latch. Don't get confused on those three things. I've tried to explain the differences between them, and Spinlock problems show up as high CPU for SQL Server with no one query causing the problem. I really appreciate your patience today. aka.ms, bobwordms is where the deck is. aka.ms, Bob SQL demos are where the demos are. And here's a lot of great resources for you, including shameless plugs for a book I've written. In fact, I've written 3 of them now. So if you want to go out and learn about SQL and Linux, 19, and now Azure SQL, you can do that. Suresh, we are like out of time. I hope you enjoyed it today. Suresh, was there just one question that stood out I should talk about, or how did it go?
Yes, Bob. I think one great question multiple folks asked is the troubleshooting methodology different depending upon whether SQL Server runs in your data center or Azure or Windows versus Linux for weights, latches, Spinlock?
Yeah, thanks, Suresh. I think the good news is this, it's all the same. All that stuff I showed you, everything I showed you today, let's take the Azure SQL away for a second. Everything besides Azure SQL I showed you today works on Linux and works on SQL Server. The engine itself, all that stuff is normal. Now, if you get into like a preemptive scenario for operating system calls for Linux, you might have some different debugging to do there. For Azure SQL, I showed you one different scenario, but a lot of the stuff I showed you as well can happen in Azure SQL. So a lot of the techniques we talked about for weights, for latches, even for Spinlocks apply, because you know what? It's the same SQL engine running across SQL on Linux, SQL 19, and an Azure SQL. Hey, we're out of time. Thank you again, Suresh, so much for being my moderator. I'm sure you answered a boatload of questions. Thank you all for joining. My email is bobward@microsoft.com. That's dangerous to tell people. If there's a question that you just didn't get answered today that you're dying to know about, bobward@microsoft.com. I'm happy to help you. I hope you enjoy the rest of the Past Virtual Summit. Thanks for attending today.